Welcome to G Fun Facts Online. Today, we are stepping into the most silent, cold, and precise room in the universe to tell a story about the most volatile substance in existence. We are talking about antimatter. But forget what you know from science fiction. This isn't about warp cores, and it's not about angels and demons exploding over the Vatican. This is about a much quieter, more profound revolution. It is the story of how physicists at CERN have moved from simply containing the beast that is antimatter to teaching it to dance. We're going to explore the cutting edge of physics as of 2026, specifically the work of the base collaboration and how they have achieved the quantum control of a single individual antiproton. Let us begin by setting the stage. For nearly a century, antimatter has been the enfant terrible of physics. It is the mirror image of ordinary matter, identical in mass, but opposite in electric charge. And it has one terrifying property. Upon the slightest contact with our material world, it annihilates. It vanishes in a flash of pure energy. This volatility makes it incredibly difficult to study. If you touch it, you lose it. For decades, the best we could do was smash particles together at near light speeds and look at the debris, or trap clouds of antimatter for short periods before they drifted away or annihilated. But the narrative has shifted. We are no longer just caging the animal. In the supercooled vacuum of the base laboratory, scientists are now interrogating individual antiprotons with a precision that rivals the ticking of the most accurate atomic clocks. Why? Because the universe is hiding a secret. The Big Bang should have created equal parts matter and antimatter. They should have annihilated each other instantly, leaving nothing but light. Yet, here we are. We live in a universe made almost entirely of matter. Where did the antimatter go? To answer this, to find the missing half of reality, physicists are looking for the tiniest flaw in the symmetry of the universe. And to find that flaw, they need to look at one single particle, alone in the void. This brings us to the engineering marvel that makes this possible, the vessel of the void, known as the advanced penning trap. To control an antiproton, you must create a prison from which there is no escape, but more importantly, within which there is no touch. You cannot hold an antiproton in a test tube. The walls would destroy it. Instead, we use electromagnetic fields. Imagine a microscopic can, no larger than a stack of coins, situated inside the bore of a massive superconducting magnet. Inside this can, the air is pumped out to a vacuum so extreme that it rivals interstellar space. We are talking about pressures lower than 3 × 10 to the power of -18 millibars. In this absolute nothingness, a combination of strong magnetic fields and static electric fields creates a potential well. Think of it as a steep valley, where charged particles are forced to roll back and forth, orbiting endlessly without ever touching the walls. For years, the gold standard was simply keeping these particles alive. The base collaboration shattered records by keeping a cloud of antiprotons trapped for over 405 days. That is over a year of holding on to the most explosive substance known to man. But quantum control requires more than a cloud. A cloud is messy, particles bump into each other. To get the precision we need a soloist. The modern trap architecture is a multi-trap system. It consists of a reservoir trap and a precision trap. Think of the reservoir trap as a holding pen, where a cloud of antiprotons harvested from CERN's antiproton decelerator is stored. Then, using sophisticated voltage ramps, physicists can pinch off a small segment of that cloud, shuttle it between zones, and filter the particles until exactly one antiproton remains, just one. This single particle, isolated in the dark cold of 4 Kelvin, which is -269 degrees Celsius, becomes the subject of the most precise interrogation in history. It orbits the trap like a tiny planet. Its motion is defined by 3 specific frequencies: the cyclotron motion, which is its rapid orbit around the magnetic field lines, the axial motion, where it bounces up and down, and the magnetron motion, a slow drift around the center of the trap. But trapping the particle is only step 1. The real challenge, and the subject of recent breakthroughs, is cooling it. You see, even when trapped in a dark, cold vacuum, the antiproton is hot. In the quantum sense, it jitters. It has thermal noise that obscures precise measurements. If you want to measure the fundamental properties of the universe, you cannot have your ruler shaking. You need stillness. Usually, with normal atoms, we use lasers to cool them. We shoot laser light at atoms to slow them down. But this doesn't work for antiprotons. We don't have antilasers, and the antiproton lacks the internal energy structure required for laser cooling. So, how do you cool something you cannot touch and cannot shoot with a laser? The solution, perfected in recent years, is a technique called sympathetic cooling. It is, quite literally, a quantum waltz between a beauty and a beast. Here is how it works. Physicists trap a single logic ion, typically a beryllium-9 ion, in a separate but adjacent trap. This beryllium ion is the beauty. It has a complex structure that allows it to be laser-cooled to near absolute zero, entering its quantum ground state where it is virtually perfectly still. Now, here is the magic. The hot antiproton and the cold beryllium ion are separated by space, but they can feel each other. Through the electrostatic force, the repulsion between their charges, they are coupled. It is like connecting two pendulums with a very weak spring. The antiproton is swinging wildly with heat, and the beryllium ion is hanging still. Over time, the energy transfers through that invisible spring. The antiproton transfers its thermal energy to the beryllium ion. The beryllium ion heats up, but we can immediately cool it back down with lasers. Essentially, we are pumping the heat out of the antiproton and venting it through the beryllium ion. This technique allows the antiproton to be cooled to the ground state, the lowest possible energy level allowed by quantum mechanics. It is now calm enough to reveal its secrets. Once the particle is cold, the team employs a method called quantum logic spectroscopy. Since we cannot easily read the state of the antiproton without destroying its quantum coherence, we use the beryllium ion as a messenger. By coupling their motions, the quantum state of the antiproton, specifically its spin direction up or down, is mapped onto the beryllium ion. We then probe the beryllium ion with a laser. If it lights up, the antiproton was in one state. If it stays dark, it was in the other. This allows for the non-destructive readout of the antimatter's secret life. We are essentially spying on the antimatter through a keyhole provided by the beryllium atom. Now, let's talk about the major breakthrough that shook the physics world in July 2025. The BASE collaboration published a result that changed the game. For the first time, they demonstrated coherent spin spectroscopy on a single antiproton. To understand why this matters, we have to understand the difference between incoherent and coherent measurement. Previously, measuring the spin of an antiproton was a bit like flipping a coin and checking to see if it was heads or tails. It was a statistical process. But in the 2025 experiment, they managed to place the antiproton into a superposition of spin states. It was simultaneously spin up and spin down. And crucially, they maintained this delicate quantum phase for nearly 50 seconds. 50 seconds might not sound like much to us, but in the quantum realm, where events happen in nanoseconds, 50 seconds is an eternity. For those 50 seconds, that single antiproton was acting as a qubit, the fundamental unit of quantum computing. By applying precise microwave pulses, the researchers induced what are called Rabi oscillations. They caused the antiproton spin to flip back and forth in a predictable, coherent rhythm. Imagine the difference between a crowd clapping randomly versus a crowd clapping in perfect unison. That is coherence. This level of control reduced the width of the resonance peak by a factor of 16 compared to previous methods. This massive jump in precision means we can measure the frequency at which the spin flips, known as the Larmor frequency, with unprecedented accuracy. This frequency is directly tied to the particle's magnetic moment. By measuring this and comparing it to the proton, we are testing the fundamental symmetry of the universe, called Kaplan symmetry, to a precision of parts per trillion. If there is a difference, even in the trillionth decimal place, the standard model of physics breaks, and we have found new physics. But the innovation doesn't stop at the laboratory door. Perhaps the most sci-fi application of this technology is the BASE STEP initiative, which stands for Symmetry Test with Portable Antiprotons. Historically, if you wanted to study antimatter, you had to go to CERN in Geneva. That is the only place on Earth with an antiproton decelerator. But there is a problem. A particle accelerator is a noisy place. It vibrates with the hum of massive machinery, and the magnetic environment fluctuates. This magnetic noise limits the precision of these ultra-sensitive quantum measurements. It's like trying to listen to a whisper while standing next to a jet engine. The solution? Take the antimatter to go. BASE STEP is a transportable penning trap system. Essentially, it is an antimatter thermos truck. It is designed to load a cloud of antiprotons at CERN, lock them in a portable superconducting magnet, and then physically drive them by truck to a quiet, dedicated precision laboratory, such as the one at Heinrich Heine University in Dusseldorf. This project relies on the extreme vacuum and stability developed for the single particle control. If you can control a single antiproton for years, you can certainly take 1 billion of them on a road trip. This opens the door to a new era where antimatter is a resource distributed to high-precision laboratories worldwide. Imagine a network of labs, all studying antimatter in perfect silence, far away from the accelerator that created it. So what is the ultimate goal of all this effort? Why spend millions of dollars and decades of time to cool down one particle? The goal is not just stewardship, it is interrogation. The standard model of particle physics is the most successful theory humans have ever created, but we know it is incomplete. It cannot explain dark matter. It cannot explain dark energy. And it cannot explain the matter-antimatter asymmetry. By comparing the charge-to-mass ratio and the g-factor, or magnetic moment, of the proton and antiproton, scientists are looking for a crack in the mirror. There are two main frontiers here. First, CPT symmetry tests. CAPTAIN stands for charge, parity, and time reversal. The theorem states that if you flip the charge, create a mirror image, and reverse time, the laws of physics should look exactly the same. If the antiproton's magnetic moment differs from the proton's by even the tiniest fraction, CPT symmetry is broken. This would imply that the laws of physics are fundamentally different for matter and antimatter, potentially explaining why our universe exists at all. The second frontier is the search for dark matter. These penning traps are so sensitive that they can act as detectors for dark matter. There is a theory that the universe is permeated by axion-like particles. If these particles exist, they might interact faintly with the spinning antiproton, causing a tiny wobble in its precession frequency. The antiproton becomes a dark matter antenna. Finally, we must look to the distant future. While the current focus is on fundamental physics, the mastery of individual antiprotons lays the groundwork for technologies that currently exist only in dreams. The energy density of antimatter is unparalleled. It is 9 × 10⁻16 joules per kilogram. To put that in perspective, a few grams could power a city. A few kilograms could send a starship to Proxima Centauri. We are, of course, centuries away from the warp cores of Star Trek. However, the techniques of high-density, non-neutral plasma confinement, essentially stuffing billions of antiprotons into a small space without them touching, are being refined alongside these single-particle experiments. Projects investigating the interactions of antimatter with gravity, like the alpha-G and GBAR experiments, rely on similar trapping and cooling technologies. Every time we improve our ability to hold and manipulate this substance, we inch closer to a future where antimatter is not just a curiosity, but a tool. In conclusion, we have entered the golden age of antimatter physics. We are no longer merely observing the destructive flashes of annihilation. We are holding a single mirrored shard of reality in a magnetic bottle, cooling it to the stillness of deep space, and asking it to whisper its secrets. In the quantum control of the individual antiproton, we find not just a triumph of engineering, but a doorway to understanding the very origins of existence. The mirror is no longer just reflecting, it is speaking. Thank you for listening to G-Fun Facts Online. If you enjoyed this deep dive into the quantum realm, make sure to stay tuned for our next episode.